So I don't know if you realize this or not, but this is the moment that you all have been waiting for. We've been learning how to find we learned what a derivative is. We learned its difference between the derivative and an average rate of change. Derivative is instantaneous rate of change. And we learned how to find the derivative using the definition of derivative, which is a fairly long, fairly involved limit process that is not easy by any means. It's definitely doable, but not easy. So, and if you've had calculus before, you already knew this, but if you didn't have calculus, this is maybe a complete surprise to you, that there is a whole set of rules that makes taking derivative easier. In other words, we can take the derivative without having to go through the whole limit process. And this sheet that you're looking at right now is the list of rules. This does not cover every single one, but this is the main ones that we'll be using. So in this list, you will be able to use for the final, but you won't be able to use it for the midterm. So you do need to learn all these, and it does look kind of intimidating, but it's not really that hard. So first of all, we need to talk a little bit about variables. I don't know if you have picked up on over your mathematical career, there's certain variables that mean certain things. For example, we usually use letters like U and X and Y, a lot of the letters towards the end of the alphabet, to represent actual variables or functions. And what do I mean by actual variables? An actual variable is a variable that could be replaced by a number of different numbers. We also have variables that are kind of like, they're constants, but they're still a variable. Meaning, like, for example, often we'll use A, B, or C that represents a number that's set, but we just don't know what it is. Like, for example, you've seen this in y equals ax squared plus bx plus c. So in that case, A, B, and C are all some number. They're not variables, but Y and X are variables. So that's what I mean by the kind of the difference between variables. And then sometimes we'll use a variable to represent a expression or a function, and we usually use U's, V's, and W's. So these things are often functions, which means they're an expression with several different possible variables and numbers in them. Then we have actual variables, which are usually like X and Y and Z and T. And then we have constants that are represented by a variable. We just don't know what the variable is yet. And those are usually like A, B, and C. So that's kind of the breakdown of the different types of variables. I don't know if that was helpful. I know it seems kind of strange that we have these different categories, but and this is not a hard and fast rule that you could use W to represent a constant. It just the context would have to explain that. So, but in this sheet, what I've said across the top here is true. We're using U, V, and W to represent some kind of expression. Actually, I think I just use U the whole time. And the variables we use are X and T. And then the constant, I always use an A. Okay, so let's see if we can make sense of this sheet. So the very first thing you see at the very top is what is called the chain rule. This thing right here is called the chain rule. So you know, when you, from pre-cal, you learned that we can have what are called composite functions. You may have seen this, f of g of x. You guys remember that? That represents a function inside of a function. And so anytime we're taking a derivative of a function inside of a function, we have to follow this rule at the top. So this chain rule applies to every derivative you'll ever take. all these other rules apply to only certain situations, and we'll explain those in a minute. But the chain rule, you always have to consider. Every derivative you take, you have to consider the chain rule. And the way what it's saying is, notice this is that Leibniz notation. This is saying that I'm taking this right here says I'm taking the derivative of u of t with respect to x. So in other words, another way to write that would be du dx. Okay. So, but the issue here is that u is in terms of some other variable t. So if we're taking the derivative of u with respect to x, but it's in terms of t, that means we're going to have to take the derivative of u with respect to x, then we take the derivative of t with respect to x, and then we take the derivative of x with respect to x, which of course this would just be 1, because dx would be 1, because we're saying how does x change compared to how x changes. That would just be 1. It's a one-to-one correspondence. And notice that we're multiplying all these. So basically you're taking derivative of the outer layer and leaving the inside layer alone. Then you're taking the derivative of the next layer and on down until you get to all the layers. So this could go on for 4 or 5 or 6 or 10 layers. Fortunately, at the beginning, we're not going to do anything really complicated like that. We're just going to do some very basic ones. In fact, the first handful of derivatives that you take, the chain rule will only produce a 1. It won't produce anything else. Okay. So let's look at some of the other rules. The first one here is pretty straightforward. This says if you're taking the derivative of a constant, because remember, a represents a constant. This is saying how does a change compared to how x changes? Or, well, if a is a constant, it's not changing at all. So the derivative is just 0. Okay, so if you're taking the derivative of any constant, the derivative is 0. So then likewise, if we're taking the derivative of a constant times some other function, remember this represents a function, u represents a function. So if we're taking the derivative of a times some function, you will get a times the derivative of that function. That's what this notation means. So I'm taking the derivative of a times a function. I will get a times the derivative function. Okay? So for example, if my function is sine x, then the derivative of that, or let's say function is 5 sine x, then the derivative of that would be 5 times the derivative of sine x, whatever that happens to be. But in other words, the 5 just kind of goes along for the ride. Okay? And then the last one on the top row, this is just saying if you're taking the derivative of 2 different functions added together, you can just take the derivative of those functions separately and add the derivatives together. That's that guy right there. Right? So those are kind of the simple ones. Those are big governing rules that affect a lot of different functions. Now we'll go to the more specific ones. So the next one here is what is called the power rule, which this is probably the one you're going to use more than any other rule. This is when you have, I forgot one. N is also a constant. There we go. So this is meaning I have some function raised to a power of a number, so like x squared or x cubed or sine squared or cosine cubed, or so this is some function raised to a power. So when you have something raised to a power, then you'd use the power rule. And the way the power rule works is you multiply the front of the function by the power, and then you drop the power 1, and then you multiply that by the derivative of the function because of the chain rule. So for example, let me erase this. If my y was sine x to the 5th, then my dy dx would be 5 times sine x to the 4th times the derivative of sine x. Okay, that's what the power rule is saying. You multiply by the front by the power, drop the power 1, and then multiply by the derivative of the inside. Now, if my function was just, sorry, that's my phone beeping. If my function is just x squared, or say x to the 5th, then dy dx would be 5 times x to the 4th times the derivative of x, which would be dx dx, which of course is just 1. So we don't really need to write that. So it would just be 5x to the 4th. Okay, so this is a case that I'm talking about where the chain rule just kicks out a 1. It doesn't kick out anything extra. Okay. All right. So that's the power rule. So then the next rule is the exponential rule. So notice that a is the base of the exponent now. Excuse me. And it's raised to some expression. So this could be like 3 to the x, or this could be like 3 to the sine x, or something like that. So you have but the base is a constant and the power is something involving a variable. Okay, so this is saying that when you take the derivative of an exponent like that, you have to multiply out front by the natural log of whatever the base is. Then you just leave this the same, and then you multiply by the derivative of whatever u is. Okay, so for example, if I was taking y equals, say, 5 to the x, the derivative of that would be natural log of 5 times 5 to the x times the derivative of x, which is just 1, so I don't need to write that. The derivative of x with respect to x is just 1. Okay? Now, if it was 5 to the 2x, well, now it's going to be a little bit different, isn't it? Because of the chain rule. dy dx is equal to natural log of 5 times 5 to the 2x times the derivative of 2x. Now, the derivative of 2x, remember, we go back up here, the derivative of 2x would be 2 times the derivative of x, right? So that, well, 2 times the derivative of x is just 2, because the derivative of x is 1. So this would be times 2. Okay. And then one more here, the log rule. This is just saying if you have the log base some number of an expression or a variable, then you will go 1 over u. So there's the, you can see the 1 over u right there. And then also on the bottom of that, you have the natural log of whatever the base of the log is. And of course, because of the chain rule, you have the derivative of u multiplied by the derivative of u. So for example, if y is equal to log base 4 of x, then dy dx would be 1 over x times the natural log of 4 times the derivative of x, which of course is just 1. So that's not very well written. This would be 1 over x times the natural log of 4 times the derivative of x, this dx dx, which would just be 1, so I don't bother writing it. Okay? Then you got a whole set of trig functions. You got sine, cosine, tangent, secant, cosecant, and cotangent. And those are just some, just like the rest, the derivative of sine in this case is cosine of u, and then the chain rule would say you'd have to multiply it by the derivative of u. So these are pretty straightforward. You just have to know, this might take a little bit of memorization. These on the top won't take as much memorization because you'll do so much practice that they'll just get stuck in your head. These don't show up as much, so you might have to take some time to memorize them before the exam, and you might as well do it right away. That way it'll make your homework go quicker. Don't worry about the arcsine, arctangent, arcsecant down here. We'll talk about those later. when we get to more complicated things. And then down here, we have the chain rule, which is already mentioned above. And we also have the product rule and quotient rule, which those are more advanced rules that we will talk about at a later time. So don't worry about those just yet. Okay. So again, just one more run through. Let's say that we are working on this and we come up across a function that's y equals sine of 2x. And we want to take the derivative of that. So that'd be dy dx. So we go up to the rule list and try to find, looks like sine is the main thing. So this says that the derivative of sine is cosine. The derivative of sine u is cosine u times the derivative of u. So I'm going to go back down here. So the derivative of sine u would be cosine u. Okay, in this case the u is 2x. Times the derivative of u, which would be 2x. So what's the derivative of 2x? That'd be 2 times the derivative of x, which is just 1. So in the end, we'd have 2 cosine 2x. Okay, one more example. Let's say we have y is equal to 5 to the 5 to the tangent x. Okay. dy dx would be, well, let's go back up here. We got an exponential rule. That's the outside function. This tells me that when I have an exponential rule, I got to multiply by the natural log of the base. The exponential stays the same, and then I have to multiply by the derivative of the inside function. So that would be natural log of 5 times 5 to the tangent x. Sorry. And then, so in this case, u is tangent x, right? So we still have to multiply by the derivative of u. So we need the derivative of tangent. So we go back up here. Where's tangent? Right there. Apparently the derivative of tangent is secant squared. So that would be secant squared x. And then times the derivative of x, which of course is just 1. So dx dx would just be 1, so we don't bother writing it. So that would be the derivative of y equals 5 tangent x. Okay, so that's a rundown of the rules. There's a bunch of practice sheets in there. I would recommend that you get a lot of practice at this. The more the merrier, because basically that's the best way to learn these rules, is just to apply them in a lot of different situations. All right, have fun. You should actually really have fun because you don't have to do that long limit process anymore. So